Welcome, dear students. Unit-3 2022 Advanced Mechanics Solution. Question paper 2022 Advanced Mechanics Unit 3. Question 4a. The Lagrangian of a one-dimensional anharmonic oscillator with unit mass is given by L equal to half x dot square minus half omega square x square minus alpha x cube plus beta x dot square. Find the Hamiltonian and show that the canonical equation of motions are x dot equal to this, p dot equal to this. This is a solution of 22, unit 3. Here, the only generalized coordinate is x. The Lagrangian L of the system is given by L x dot equal to half x dot minus half omega square x square minus alpha x cube plus beta x dot square. The conjugate momentum P corresponding to x is given by P equal to del x dot L. So this is equal to x dot plus 2 beta x dot. And hence x dot equal to P by 1 plus 2 beta x. Equation 1. Therefore, the Hamiltonian H is given by H equal to Px dot minus L. Px dot minus L is this. So putting the value of x dot here, and after simplification, we get H equal to P square by 2 into 1 plus twice beta x plus half omega square x square plus alpha x cube. And this is the required Hamiltonian. Second part, the Hamiltonian canonical equations of motion. So x dot equal to del ph and p dot equal to minus del xh. So del ph equal to now from the equation h, from the equation 2, this equals to p by 1 plus twice beta x. This equals to x dot. And del x dot is equals to del x h is equals to with respect to x. So this omega square x plus 3 alpha x square and this whole square minus p square into 4 beta by this whole square. So is equal to minus beta x dot square plus omega square x plus alpha x square. And by 4 we here use the x dot equal to p by 1 plus beta x. So 1 plus 2 beta x equals to this p by x dot, and p cancelled, so we get this. And hence from 3, this 3, we get x dot equal to p by 1 plus beta x. Actually, we get from 4 this, and p dot equal to this, p dot equal to, so beta x dot square plus omega square minus omega square x minus 3 alpha x square, and x dot equal to this, p dot x equal to this. Is the required result. Next question, question 4b. A particle of mass m and coordinate q has the Lagrangian L equal to half m q dot square minus lambda by 2 q dot square, where lambda is constant. Find the Hamiltonian and deduce the Hamilton's equation of motion. We have P equal to del q dot L. P is the corresponding momentum corresponding to q, and so this equals to mq dot minus lambda q dot, because L is this. So q dot equal to p whole divided by m minus lambda q. In the Hamiltonian H is equals to PQ dot minus L, and put this and substitute the value of Q dot here. So we get the Hamiltonian H equal to half P square by M minus lambda Q. And the Hamiltonian equation of motions are given by Q dot equal to del del PH and P dot equal to minus del del PH. So Q dot equal to P by M minus lambda Q and P dot equal to minus P square lambda by 2 into M minus lambda Q whole square. Next question. C. State and prove the principle of stationary action. Obtain the modified Hamilton's principle from the principle of stationary action. Principle of stationary action or principle of least action. The principle of stationary action for conservative system is delta W equal to 0, where W equal to integration T1 to T2 summation over K Pk Qk dot dt is called abbreviated action. Now, proof of this stationary action, principle of stationary action, consider Hamilton's principal function or action integral S equal to integration T1 to T2 L dt. The delta variation of S is delta S equal to delta integration T1 to T2 L dt. This delta equal to small delta plus delta T into ddt. This integration T1 to T2 L dt. So small delta integration T1 to T2 L dt plus integration T1 to T2 capital delta d of L. So this is equal to L delta T T1 to T2 because this delta dt equal to 0. So we can write this delta integration L dt equal to this delta L dt because delta dt equal to 0 from this here. So delta capital delta S equal to integration T1 to T2 summation over K, and this delta L we can write del del Qk L delta Qk plus del del Qk dot L del Qk dot into dt, and this L delta T lower limit T1 to T2. In the present case, delta Qk not equal to 0 at the endpoints, hence delta integration T1 to T2 L dt is not equal to 0. And now, according to Lagrange's equations, we have ddt of del del Qk dot L minus del del Qk L equal to 0, or this equal to equation 3. So, also delta Qk dot equal to ddt of delta Qk. This Qk dot is ddt, so we can interchange here delta and ddt. Using 3 and 4, the quantity in the first term of Q2, first term of 2, this we can write del del Qk L delta Qk del del Qk dot L delta Qk dot is equal to ddt of del del Qk dot L delta Qk plus del del Qk dot L ddt of delta Qk. So this ddt of del del Qk dot L delta Qk, and this equal to ddt of Pk, actually del del Qk dot L equal to Pk into delta Qk. Also, capital delta Qk equal to small delta plus delta T ddt, because this capital delta operator is this given by this. So delta Qk plus delta T into ddt of Qk. So delta Qk equal to capital delta Qk minus delta T into Qk dot. This Pk delta Qk equal to Pk capital delta Qk minus Pk Qk dot delta T. Equation 6. Hence del del Qk L delta Qk plus del del Qk dot L delta Qk dot, and this equals to a ddt of Pk delta Qk minus ddt of Pk Qk dot delta T given by 6 is the 6. Thus equation 2 is given by delta is equal to delta integration T1 to T2 L dt equal to integration T1 to T2 summation over K and ddt of Pk delta Qk minus ddt of Pk Qk dot delta T whole into bracket into dt plus L delta T lower limit T2 to T1. So after simplification, we get expression 8 at as delta qk equal to 0 at the endpoints. So pk delta qk t1 to t2 equal to 0. So equation 8 reduces to capital delta integration t1 to t2 L dt is equal to L minus summation over k pk qk dot into delta t t1 to t2. So this is equal to capital H minus capital H delta t t1 to t2. If we restrict to our system for which del del t h equal to 0, that is h is independent of explicitly independent of t, for variation for which h remain constant and conservative system, and then capital delta integration t1 to capital H dt, this equals to t1 to integration capital H d into delta t. So this is equal to capital H delta t t1 to t2. Substituting this in 9, we get capital delta integration del t1 to t2 L dt equal to minus capital delta integration t1 to 2 capital H dt. So we get this H plus L dt integration equal to 0. So delta integration t1 to t2 summation over k pk qk dot dt equal to 0 because H equal to summation pk qk dot minus L. And this is the principle of stationary action. The quantity integration summation t1 to 2 summation over k pk qk dot dt equal to capital W is known as Hamilton's characteristic function. Next part, modified Hamilton's principle. The Hamiltonian capital H for a dynamical system is given by capital H equal to summation over k pk qk dot minus L q dot t. According to Hamilton's principle, delta I equal to delta t1 to t2 L dt equal to 0. Thus, delta I equal to delta integration t1 to t2 is summation of pk qk dot minus h qp t dt equal to 0. This is known as modified Hamilton's principle. In case of Hamilton principle 1, and this is the Hamilton principle, and this is the equation 2 is the modified Hamilton principle. The refers the configuration space and the variation of path allows for the variation in generalized coordinate qk at constant time t. In case of modified Hamilton's principle 2, the integral is to be evaluated over the path of the representative point of the system in phase space, and qk pk are to be treated as the independent coordinates in the phase space. Here, small delta variation implies independent variations of both qk and pk at constant time t. Next question, question D. A particle of unit mass is projected so that its total energy is capital E in a field it is moving in and the potential energy Vr at a distance r from the origin. Using the principle of stationary action, so that the differential equation of the path is this, where c is an arbitrary constant. Question D. Here total energy is capital E and the potential energy is capital Vr, function of r, where r is the distance from the origin. Then by the energy equation, capital H is equal to T plus Vr. H is independent of time t, this is equal to total energy E. And T is the kinetic energy and T equal to E minus Vr. Now the action A is given by A equal to integration T0 to T1 twice T dt, and this integration over S S0 to S1 integration 2 whole E plus E minus Vr into ds. This is the E minus Vr, and this and dt change to ds because we have this ds equal to root over r square theta square plus dr square. We change ds to dr by this formula s0 to s1. So this is equal to s0 to s1 integration f of r d theta dr into drc. We see that theta is ignorable. So from the principle of stationary action, this delta A equal to 0. So we have the dr of del f del theta dash equal to del theta f. Theta dash equal to ddr theta. Here a is a function of r and theta dash. So DDR of del del theta dash f is equals to 0 because del del theta is equal to 0 as f r theta dash is independent of theta. So del del theta dash f equal to root 2c constant say. So this integration del del f theta. So f is the function is this, f is the function is this, say f r d theta equal twice e minus vr 1 plus r square d theta dr whole square. So del del theta dash f equal to, because f is this, we get this equal to 2c. After simplification, we get this result, this. Note that here 2t dt equal to 2t dt ds equal to 2 ds dt ds. So twice the q dot ds dt equal to q dot t equal to half q dot m q dot square. So q dot equal to root 2t. So m equal to 1 here. So this twice t by root 2t into ds. So twice t dt equal to square root of 2t ds. This is the square root 2t of ds. So this 2t dt equal to square root 2t ds. The explanation is here in the note. Thank you for watching this video, and the note of this PDF is given in the description box.